Great. So first of all, I'd like to thank the organizer very much for the invitation to speak here and expose my work as a newcomer to the field to a broader audience. I really appreciate that, and I hope you'll find what I'm doing interesting. So what are Specht polynomials? Let's begin with some basic definitions. The symmetric group is well known for a long time such that all its irreducible representations over characteristic 0 are associated with the Specht models, and they are corresponding to partitions of n, which I denote like this. And this is the fact as abstract representations, and the Specht polynomials and their generalizations amount to realizations of these representations in this ring, in the ring of polynomials. It has a natural action with the symmetric group by interchanging the variables. I look at it as a graded ring, of course, and the action preserves the grading, and we are interested in realizations of these Specht models on QXN. I denote it like that. Okay, so like everything in the representation theory of symmetric groups, we work with Young tableaus. So SYT is, as usual, the set of standard Young tableaus, which the content of them is the numbers 1 to n, where lambda is a partition of n. They have to increase both to the right and below. The number of these tableaus is called f lambda, and it's equal to the dimension of s lambda. And I use SSYT for semi-standard Young tableaus, where here it's relaxed a lot. First of all, the content is allowed to have zeros, and we demand weakly increasing towards the rows and strictly increasing in the columns. Now, there is this subset CCT of lambda, which will show up a bit later. It's a subset of SSYT of lambda, which is in bijection with SYT of lambda, and these are the minimal destandardizations. I mean, the destandardization is pretty much the process that Professor Cortel showed in her talk, and CCT of lambda are the minimal ones you get from the standard tableaus. Okay, so for each such tableau, you have the row column and the row group, subgroup and the column subgroup, R and C. I mean, they're different from the R and C we saw in the previous talks. These are sometimes called Young subgroups. And the model, the abstract model S lambda, is generated by a basis associated with the standard Young tableaus. And it comes with a natural property that if we let an element from CT act on ET with the same T, then the action is through the sign character. And how do these things look in practice? If T is this specific tableau, then the row subgroup interchanges these 4 numbers with one another and these 3 numbers with one another and leaves 6 as it is. And the column subgroup interchanges these. It might interchange these 2, or it might interchange these 2, and it leaves 7 as it is. Okay, so this is how this group look like. And okay, this is again the same tableau and the same RC and sigma ET. And the Specht polynomials, before I put higher or generalized, is the following product. You take all the columns of T, and in each column you take all the pairs and you take the product of the differences. This guy I call FC0T for reasons that will be clear below. And in this example is, I don't know if this hides the part of the slide. So it's x3 minus x1, 6 minus x1, x6 minus x3, x5 minus x2, and x8 minus x4. For each column, all the pairs that lie in it. And the very classical theorem by Specht, Peel, Murphy from the 30s or below or before that, we fix lambda. We run over all SYT of lambda, and for each such element, we take the corresponding Specht polynomials. Then they are linearly independent, and they span a subspace of the space of polynomials of the fixed degree. And this space is isomorphic to S lambda. This space is Sn invariant, and it's isomorphic to S lambda. So this is the realization. Now, the higher Specht polynomials are additional copies of S lambda that were constructed originally by Ariki, Terasoma, and Yamada. because it was well known that the co-invariant ring, whatever ring it is a regular representation of Sn, and the higher Specht, the usual Specht polynomial is only constructed one copy of S lambda, and we know that the regular representation has to contain F lambda copies, and they constructed the others. And I will show now how this is done. So the definition that I'm going is already to the generalized case because it's not more complicated than the higher Specht polynomials that aren't generalized. It goes as follows. We take a monomial and we let the Young symmetrizer act on it. The Young symmetrizer is this guy, which is very well known to anybody working with symmetric groups. And we need to let it act on a monomial. So I take T, the one giving us epsilon T, and I take M. So since T has content elements from 1 to n, then it provides us an indexing for the boxes, and I denote Vt of I for the box containing I in T, and then M of V, where M is some semi-standard Young tableau, is simply the value in this box V that shows up in M. For example, if I is 5, then this is Vt of 5, and this is the same box, so M of this box is 2. And I run over all the indices. I take the, for each index I take the power I put for xi in the monomial is, I take the box Vti, I take the M of it, and take the product of all of them. So for M and T and M, these guys will get this monomial. And the generalized higher Specht polynomial is the following. You take this monomial I just constructed, and I let the Young symmetrizer act on it, but I divide by this number SMT. It is the stabilizer, the size of the stabilizer in RT of this monomial, which simply gets rid of a factor, but this getting rid of this silly factor is something that will play a role later. And a theorem which is pretty close to what happens with the usual Specht polynomial is that when I fix M, the span of these where T runs over the standard Young tableaus is again a copy of S lambda in the same manner. Now the higher Specht polynomials without the generalized amount to doing exactly this construction when I restrict M to CCT, and I don't divide by SMT. That was sufficient for their purposes, but we'll get more. Okay. One property of these polynomials is the following. Instead of taking CT and recalling that we have the action by the sign, we take the normalizer of CT by inside Sn. I call this C tilde T. And there you are also allowed to interchange full columns. So for example, if this is CT, I also have this element which interchanges this column with this column, where the columns have the same length, of course. And this contains CT as a normal subgroup and as a factor in a semi-direct product. And then and in this semi-direct product, we have a character sign tilde. And what happens is that these FMT are acted by this larger group through this extended character. So once we know this happens, this is independent of M. Once this happens, we can take the quotient, and this quotient is C tilde invariant, and the result that we could prove with my master student is that if I restrict to a particular subset of the CCT, then these quotients and the usual symmetric functions that are invariant under everything, they generate the full invariant ring under C tilde of T. Okay, so this is one thing. Now, the reason why something that comes out of dividing by SMT is the following, that we can go from n to n plus 1 in the following natural manner, which means from each lambda, I increase it by simply extending the first row. For the standard Young tableaus, I put the next number in the new box. And what I do for the semi-standard Young tableaus, I call this iota hat of M, is I move all of these, I move one box to the right and add another 0. And everything below remains the same. Everything below the first row remains the same. So what happens with this construction is that sin is the following. If I take the polynomial with the larger parameters, with n plus 1 variables, it will reproduce the one with m and t once I kill the last variable. Now, this is a very useful property, and moreover, this property will eventually determine the extended polynomial in a manner that I don't want to explain, because in 15 minutes you can't explain too much. And the fact that I divided by this SMT is crucial for this property. Like Ariki, Terasoma, Yamada don't get that with their elements, with their polynomials. Only this normalization does it. Now, this property resembles what happens when in the theory of symmetric functions, and it gives an embedding of polynomials in n variables to polynomials in n plus 1 variables. In representations, it produces a lot of stable representations, and I want to exemplify this, and combining this with the theory of symmetric functions, I will also get not only stable representations but also limits of stable representations and infinite groups. I'll give the simplest case, which I think is probably well known, though I didn't find it formulated in this way in the literature. And it goes as follows. If I take fix d and I take SSYTD of lambda, which is the semi-standard Young tableaus having entry sum d, then these representations for these m span all of this guy as a direct sum. So this is a decomposition of qx and d into Specht representations, into these irreducibles in a specific manner. And the thing is that when n is large enough, this iota hat map is a bijection between SSYTD of size n and SSYTD of size n plus 1. And this combines with this construction going from mt to iota t hat iota m, gives you a stable representation. It's also known as finitely generated Fi module. I only said this case here, but in the work itself, there is a lot of other families where all the notions of descents and compositions and all of them show up in a lot of different families. But here I only want to give one example because the time is short. So how do the limits look like? We have these two infinite symmetric groups. One contains all of them. These are only ones with a finite support. They're different, but for my purposes, they're the same because their representations are the same. These are just polynomials and infinitely many variables. This is the usual ring of symmetric functions, and these are the rings of eventually symmetric functions or almost symmetric functions, which means that it becomes symmetric after you ignore finitely many variables. And this is the ring that plays a role in what happens. And the algebraic property is that it's generated inside inside the formal power series. It's generated in an algebraically independent manner by polynomials and symmetric functions, and representations inside it are the same for Sn and S infinity, this restriction to finite finite support. So for me, this is why I say that for me, these groups are the same in terms of their representations. Now, how do the limits look like? We construct infinite tableaus. I allow a first infinite row, but only the first infinite row. We define a natural notion of standard Young tableaus for these type of things, and also semi-standard Young tableaus. Here I have infinitely many zeros, but I allow finitely many non-zero entries that may show up here at the end. If you remember, our first m was 0025. Where was it? It was here 0025. So I still remember these 2 and 5 as if they show up here in the end. And these are the notions relevant for this construction. And what we're getting is that there is a natural way to construct elements of these eventually symmetric functions that are in the same construction of the usual generalized higher Specht polynomials. These are the same objects that you will get from inverse limits like this, like in the theory of symmetric functions. When you fix m hat, you get an irreducible representation, really irreducible one. And the type of these irreducible representations depends only on the shape, just like in the finite case. And what happens is that I'll just get to the final result for this particular case. We take a similar sum like that. We get it looks the same as the direct sum we had before, but now it doesn't give all of lambda tilde d. It just gives a sub-representation, and this representation is the maximal completely reducible one. To exemplify how it is, I'll say what happens when d equals 1. When d equals 1 in the finite case, where n is at least 2, you have two irreducible representation, one constant, one trivial with the E1, and one of codimension 1, which is the trace 0 linear polynomials. Now, if I take the limit, then in this guy here, I get again E1 as the constant, but it lies in lambda. It's no longer a polynomial. And this guy here, the trace 0 linear polynomials in infinitely many variables, is again of codimension 1 in the general linear polynomials in infinitely many variables, but it has no complement as a representation. And this is the maximal completely reducible sub-representation of lambda tilde 1. Lambda tilde 1 is just this guy plus E1. But it happens for every d, and the other constructions give different constructions for these guys, different decompositions, each with its own interest. There are a lot of different families happening here. And I also conjecture about the structure of the full lambda tilde d with I don't know exactly how to prove that, but in all the cases I checked, it behaves in the way I think it behaves, that we get a filtration for lambda tilde d with subquotients that are the maximal completely reducible subrepresentations in each step, and they have explicit descriptions similar to these guys. So these are the results in a sketch, and if you want to see what they are, there are these three papers that I uploaded this May. And thank you very much for your attention, and thanks again for the opportunity to speak here.